And so that's where this equation comes from, and you will see it in your textbook. I've written it shorthand here. The shorthand way to think about this equation is with KE. KE equals 1 over 4 pi epsilon naught, which you saw in the prior slide. KE can be simplified and is often simplified and used to this value here, and you're free to use it. So this is the electric field of a point charge, KQ over R squared. That's it. That's the electric field of a point charge. By point charge, we mean a charge so small it's considered to not take up any space. The point charge has no dimensions, and it's just considered a point. Often with net electric charges, when we get far enough away from them, if I had 3 charges here near it, I could not use this equation, but if I get far enough away, I could approximate this net charge to be a point charge, and that it has no dimensions, far enough away. So when we think about electric field, you can see that I have vectors at each distance away from, each radius away from this point charge. The vector has a certain length, and as we move away, that vector gets smaller because the radius is getting larger. That makes the electric field smaller. We draw electric field lines, we just connect them out like that, and that's how we would draw an electric field line, but at each separate point it is its own individual vector. It extends radially in all directions, and the sign is determined by the coordinate system. Notice here I have the electric field for a point charge in space in all directions. It's radially outward all directions. Since this is a positive charge, you see the electric field lines pointing away. Well, I get the sign of that electric field from the coordinate system, not from the sign of that charge. The sign of the charge tells me the direction of the field. Once I get the direction of the field, then I just look at the coordinate system to figure out the sign. Q is the value of the charge, and R is the distance. We always insert it in meters. And here's the units of electric field again, newtons per coulomb or volts per meter. So I want you to consider for a second, does the magnitude of the electric field due to a charge depend on the charges around it? And the answer is no. When I look at the electric field, it depends only on that charge. If there were other charges nearby, they would have their own electric fields that would contribute, but this electric field from the single charge has a single value dependent upon that charge and the distance away from that charge we are. The direction of this electric field doesn't depend on other charges nearby either. The direction, since this is a positive charge, will always point away. Even if there's a positive charge here and a negative charge here, this positive charge will always have electric field pointing away from it. This positive charge will have also have electric field pointing away from it. This negative will have electric field pointing towards it. But I would add those like vectors. It doesn't affect the electric field of that single charge. If Q is negative, we would get these vectors pointing inward rather than outward. So we can look at the electric field of just a single proton here. What's the value of electric field? 0.529 angstroms away from the proton. This is a typical distance of the electron in a hydrogen atom. So when you think about a hydrogen atom, there's a proton here, and there's an electron that has its own cloud, but we're just looking at the proton by itself. And we're going to choose a radius here of 0.529 angstroms. Angstroms is 10 to the negative 10th meters. That's what an angstrom is. So when I can just use the equation, the electric field due to a proton is going to be KE, so that's 8.99 times 10 to the 9th, that's KE. Q is the charge of the proton. The charge of the proton we know is the elementary charge, 1.6 times 10 to the negative 19th coulombs. And I would divide that by the radius squared. So we're going to take 0.529 times 10 to the negative 10th and square it. When you run those numbers through your calculator, you get a value of 5.14 times 10 to the negative 11th newtons per coulomb. That's how big that electric field is due to a proton, the distance of an electron away in a hydrogen atom. So it's not very large at all. That's a pretty small field